Good afternoon, everyone. I'd like to thank the organizing committee for the opportunity to present. So today I'm talking about the wireless power beaming systems. The focus of the program and the discussion would be mainly on the various types of wireless power beaming technologies, and also component sets that would allow various modalities to come true. So if you go through this chart, these are various wireless power modalities. On the left-hand side, you see the inductive and capacitive short-range wireless power transmission technologies, which are really prevalent, highly efficient, high power, and currently commercially very successful. And then you have the microwave, which are really the kind of the workhorse of wireless power beaming up to date. Millimeter wave is coming through, and we'll talk a little bit about that, why you want to go down the millimeter wave path at the higher frequency range, and the pros and cons with that. And also the optical version, which effectively is the lasers, much more collimated beam, a lot more power, and also the constraints by which you would use the lasers of obviously higher energy density per beam, and so you need to kind of control that, as well as make sure you point and track it in the right way. So each one has its own trade-off, or each one has its own benefit, and it really depends on the operational use that you would choose either one of these categories. So if I go back to in history, this is Bill Brown that actually really pioneered the word Rectenna, as well as a lot of the wireless power beaming as we know it on the radiative side. So, and I picked up a few of these that are really kind of important demonstrations that you can see how far back and how visionary some of these tests were. So in 1963 was the first demonstration, all at 2.4 gigahertz, and which was effectively a transmitter with a dish focused on a horn and a rectenna, and 100 watt was transmitted in the lab. This followed up by in 1964 to 1968 with a helicopter demo, which was done outside, which was hung on a pillar about 18 meters range and put almost 10 hours of flight, which is still very, very impressive. And then in 1975, the most efficient demonstration, which was a very carefully conducted experiment at 2.4 gigahertz with an end-to-end efficiency of 54%, focusing the entire beam into a captured array of rectennas, highlighting 485 watts of DC power. 1975 was yet another high long range as well as high power, 34 kilowatts of power. And you can see the array was on top of the hill with the lights turned out, and using a 25-meter dish that was used for the demonstration of the parts. So now we go into the millimeter wave power beaming system architecture trade-off. So the question was, okay, what is the difference between all of these systems? Why would you want to choose one versus the other? So one of the, so there are many different discussions here, and the people are that have used different technologies with trade one for the other. So as a result, I thought, okay, maybe it's better to compare apples to apples. So in this particular case, what we're looking at is, let's just say 2.4 gigahertz and 5.8, which are the prominent frequency of operation for wireless power. And then 20 gigahertz, 30 gigahertz, and 92 gigahertz, these were the variations. Transmitter power, I said, okay, let's just go with 100 kilowatts, which is a reasonable high power transmitter. Antenna sizes 2 meters, 5 meters, and 10 meters in diameter, which really is getting at a 10-meter level. It starts to get really large, and the application space starts to become limited. We receive antennas, fixed it at 1 meter, and said, okay, for 1 meter, you can have it both tactical and non-tactical. And a range of 1 kilometer, for all intents and purposes, that's a number, but that's usually what, you're kind of out of enough range that you could value energy being received at that kind of range. Atmospheric loss, I put in 0.2 dB per kilometer for the worst case for all of them, and then calculating beam width, area of coverage at range, and antenna gain that are kind of the main attributes for the system calculation. So on the left-hand side, you see all the differences. What is the transmitter criteria? Is it a solid-state power amplifier? Is it traveling wave tube? What the antenna size is? So you want to gain is free with the antenna size. So you want to go as big as you can, as you're allowed to. And then the antenna efficiency and pointing and tracking. On the other side, on the receive side, you want to make sure the capture area is as big as you can get it, and so you don't have spillover radiated power. So going to the next charts, you can see these are transmitter frequencies on the x-axis and antenna beam width on the y-axis. So you can see as you go with a higher and higher frequency, generally the antenna beam is narrowed, which is obviously the physics. So you calculate that, and you'll see that you always push the higher frequency, so you have much more of a somewhat of a collimated focused beam. At the same time, the antenna itself, the transmitter antenna, is helping you by going larger and larger, which gives you more gain, which more focus. So you can drive the energy in a longer distance on the transmitter. At the same time, the spot size is also kind of the variant of the same as the antenna beam. So spot size on the target at the kilometer away. You want to be at the higher frequency because the spot size is smaller, so your rectenna is smaller, so it's lower cost. So instead of having a huge rectenna trying to capture a beam that is diverging. And also the same thing is that, of course, the bigger the antenna, the better. So in kind of the gist of this would be is that you really want to be at the high frequency, and you want to have as big an antenna as you can have for these wireless power systems. So this is, if you look at received power with some calculations and range from 200 to 1,000, you can see that you really want to be at the higher frequency. If you have 100 kilowatts, and as you're coming in, obviously, as the range increases, you're going to have loss. You're going to incur loss and divergence, but that's much less affected if you're at the higher frequency. So just that fact is more important than the quality factor for the devices you would use for the transmitter and receiver. So because your free path losses are much higher than anything you can get on the components. So in short, millimeter wave is a good place to be, and the components are now available. And regulatory limitations are better because nobody works at kind of millimeter wave just yet. And at 2.4, 5.8 gigahertz, it's a very crowded space. And safety concerns, there are a lot of studies have been done at the 92 gigahertz on the non-lethal repel effect that 92 gigahertz has, and nothing has been found. So there is opportunities there. So if you look at the microwave-based wireless power beaming demonstrations to date, where the zone of range versus DC power delivered, they're really scattered around, but the zone of interest to a large extent is somewhere between the 100 meters and 10 kilometers. Obviously 10 kilometers, it gets much harder, and the laser power beaming will do much better in that kind of range. But that's a kind of an interest where you're at, some of your systems are out of reach and you want to power them. Obviously point to point is a really important one. And some of the good demonstrations that we talked about, the 48% or 54% efficiencies, and also ground to air, and the kind of a large power delivery of 34 kilowatts is all highlighted here, and you can see that. But it's interesting that majority of these are 2.4 and 5.8 gigahertz. So what would let's say a tactical system, a much more compact system look like? I mean, in reality, these boxes are all, whether it's a point-to-point or a tactical, are all the same. The question is how far you drive each one and to make them more compact. So on the transmitter side, you have the exciter, you have some kind of phase control to make sure you have a coherent beam coming out. And then you have your driver amplifier to drive your power amplifiers to saturate that and have a higher efficiency. And then you hit your antenna, and then you are out of into the free space. The thermal power supply not to be negated, because that actually drives the entire system size, and the bias control and feed always it gets much more complicated than people give it credit to. On the receive side, the game plan is to be much smaller and lightweight. So you have the antenna, you have the impedance network and rectifier. So you have this tank circuit in the middle to make sure RF comes in and DC goes out to the load. Similar story with thermal management and energy storage in this case, where what would you do with the energy once you collect it? So there are trade-offs, and it really depends on the operational space. So looking at the millimeter wave, there are many solid state and traveling wave tubes. I mean, at Raytheon, we have built many of these, and they are very nice high power systems. These are traveling wave tube. We have built traveling wave tubes, but these are mainly Gyrotron-based 100 kilowatt systems and 92 gigahertz, and also a solid state. And some you can see that in here, the 7 kilowatt system at 92 gigahertz. So obviously, power density is very high. The beam width, as we discussed, is really small. So the watts per centimeter square is high. There are no interference to other systems at this point, which is a key advantage. So regulatory issues are much more relaxed. I mean, nothing is easy, but it's much more relaxed than 2.4. To some degrees, all weather, as you can see through dust and fog. Obviously, you have some attenuation, but it's not very high. High power millimeter wave transmitters are sort of be leveraging some other work that was done for non-lethal effects, and here, and also the safety is built in, partly because it's, a lot of studies have been done for these non-lethal effects, and now they're safe for exposure. So there are exposure limits that are safer for operations, which would be very useful for power delivery. So these are the systems we have built for, not to go through it too many times, but you can see that we started in, the first deliveries in 2000s, circa system 0, which was a 2000s, was a 100 kilowatt system, static system. That system went into a mobile system called system 1 in 2004. System 2 is really the workhorse, is all self-contained, generator, all the pieces are in there in a single truck, 100 kilowatt, and you can just drive it and turn it on and fire it. System 1R is a more compact version of the System 2. And then in the recent years, we've worked on the solid state active denial technology, which is essentially the solid state version of a transmitter. This is a much more compact tactical system, and you can play games with it somewhat and change the aperture density, because it's all solid. It's a single array of transmitters with some phase control on the aperture. So on the Gyrotron-based systems, as you can see, I mean, the Gyrotrons, how much power can we get out of these transmitters? Well, I mean, in this particular case, we went for a 100 kilowatt system, and to get range up to 1 kilometer for the power densities that we were after. But the Gyrotrons are a phenomenal system, and they get better at somewhat higher frequencies. And you can see the plot on the right-hand side, you can get up to megawatts, 1.5 megawatts plus to 2 megawatts at these frequencies and higher. So I think that the future for that is, I mean, they're much more cumbersome to use. They need superconducting magnets, and obviously the cooling that requires for those are also takes a lot of time. So it's not much the RF or the millimeter wave transmitter side of it, is more what's the supporting equipment that goes beside it. But in general, they're about 40 to 50% efficient. By the time you put it all together, the efficiency drops somewhat. But nevertheless, they are extremely useful, and coupling that to an antenna in this particular case allows you to go a long range. For a solid state, as you can see, these are the modules, very scalable modules. At the bottom side, you can see this is a W-band array of an 8x8 output waveguides of a 10-watt submodule, and these submodules get combined to become a 100-watt module, a 4x4 version of those. And then those 100-watt modules then array again to 8x8 modules, and you're in the 7-kilowatt range at that point. And this is an amazing tool. I mean, for me, this is like having 8,001-watt W-band mimics operational in a single aperture is a really amazing tool, and it works great. And you can see here what we have is that we've radiated a panel, a graphite panel that we can beam shape it by combining the beams and phase controlling it. So you can see we can almost paint power across a target, in this particular case a graphite target. So you can then observe it using the IR camera because you're putting power on target. So effectively it heats up and you can see it. And this is the kind of the smiley face that we've done just to kind of prove the point on that. But it is a very interesting and powerful system. So how far can we go? What are the other systems, and what can be done on the directed energy sources? So effective range, we have so effective power, output power on the x-axis, and effective range. So you can have high energy lasers are really important these days. They're coming along really well, anywhere between 10 kilowatt to 100 kilowatt systems. Active denial systems can go from 100 kilowatt to, let's say, tens of, almost 10 megawatts, somewhere in that range. And electromagnetic pulse units, those are really high sharp pulses, but still, if you build the rectennas matching those, you could do some work on there. And these are sources. If you look at, for example, now effective ranges, much higher effective ranges, solar systems that are on ISS, you're talking about 27,000 square feet of solar panels to get you somewhere in the bit of, hundreds of kilowatts. And then satellite RF transmitter, from GEO, for example, 100,000 kilometers away, you can get down to like, a few kilowatts. So there are sources out there that could be used for power delivery. Now, what about what does power beaming as a whole land in the middle of all the power sources, if you want to call it? And how would you qualify those? So there's a volumetric specific energy, which is watt-hour per liter. This is essentially the volumetric quality factor for an energy source versus a weight quality factor, mass-specific energy. How many watt-hours can I get per kilogram? So you can see on the supercaps, you're kind of low on volumetric, but you're also low on energy as far as mass and energies. But then as you build up the batteries kind of are in the middle range. But then once you get to the to actual fuels, you start to have a huge amount of power density, and per unit kilogram and per unit liter. So that would be that's why obviously oil is very, very sought after. Now, if you look at the 100 kilowatt W-band system, that kind of lands in the middle of all of that. So power beaming actually provides you kind of an oil-based chemical energy grade of energy, because you're transferring power from one point to another, and that range transfer kind of almost negates the amount of power that you have on the transition side. So that range will allow you can deliver power from point A to point B and receive it. As a result, you end up having a huge amount of power at your disposal. So how would you design on the receiver side? What would be the best option? So receivers are generally, obviously you can have arrays of antennas, printed antennas on the right. And they're very useful. You can have them thin film, you can shape them across any structure. And the higher the frequency, the harder this plan gets. because the diodes get a lot closer together, antennas get closer together, and diodes get, so that thin film essentially gets filled with diodes. The reflector-based one is much more kind of palatable in that way, where you can reflect the side, you can collect the power from across a large area and then focus it into a Rectenna circuit. That allows you to also be insensitive to some power variations, because you're much more of a, you aggregate power rather than being specific. So you won't burn out your receivers if the power density goes high. So on the receiver block diagram, obviously most important, I mean, you know all about this. So you've got the antenna array, you got your input filter to stop RF going out. You've got your rectifier component, which is really important because that's your quality factor for the Rectenna, and then your output filter, which allows your DC to come out. But on the other side, your load conversion circuit as to what load you need is really important. The diode is a two-terminal device, which means the output and the input are connected. It's not like a transistor where you have an isolation between the input and the output. So whatever load you put in will change the effect of what the rectifier is. And then, of course, the supercap and the high energy density array are where you would put the power. If the power is coming in at a really short bursts with high intensity, what do you do with it? How would you either use it or store it? So as far as Rectenna circuits, I mean, I won't go through this, but as you can tell, there are many different Rectenna topologies to use, and really they all home in on the fact that you need an input filters to stop any harmonics going out of the antenna, which allows you to then create a tank circuit to only push out the DC component, so the wave shaping of the internally to the diode, and then provide a DC load, the charging circuit, and a battery. But as far as the Rectenna topologies, there are many different Rectenna topologies, and there's a trade-off. So the more complicated you make the tank circuit, the more efficient it is, but that's more of a low frequency terminology, because the more components you add, the W band, for example, the more loss you incur. That means that efficiency that you gain is somewhat traded off with the loss of the components. So generally, if you look at most exquisite W band or millimeter wave circuits, are very simple in topology. And because the transmission line losses are much higher than it would be at X-band, for example. So these are some of the, I mean, I won't go through this, but you can see thin film structures that are structural are very prevalent and also easy to build. And you can see on some of these printed circuits versions in 2.4 all the way up to 8.5, highly efficient and also low weight. So that is definitely a very great lower frequency microwave work that needs to be done. And this chart, which highlights all the Rectenna tests that have been done to a large extent, and I'm sure there are more to be added to this chart. So this frequency versus efficiency. So this would be actually kind of and also input power handling. So these are the two criteria that the Rectenna circuit needs to hit. Obviously, high efficiency, good power conversion, and also high power input power handling. And the reason for that is that you can get a detector that is 90% efficient, but it will only detect microwatts. But you want watts to power handling to be able to actually see something DC power that would be useful to you. So you can see the slope is obviously efficiency is lowered as you go to a higher frequency because the losses are higher, in circuit losses are higher. But the input power handling somewhat is flat across the frequency range, which is kind of interesting because the trade-off at the lower frequency is that because you have your lambda over 2 spacing is pretty large, so power density of the transmitter is not quite correlated to the element size. But at millimeter wave, as the lambda over 2 spacing shrinks, the transmitter power that has been so far reported has not been very high. So we're trying to push up into the top right-hand side, increase the efficiency of the W-band circuit, as well as highlight the input power handling, which results into obviously high power coming out of the Rectenna. So how would you do that, and what's stopping you? And in a large extent, if you look at top right-hand side, this is your diode model, equivalent circuit model. You want very, very low capacitance, and by the only way that we can reduce the capacitance is by making the diode smaller. By making the diode smaller, you're going to increase resistance of current going through it, because now the current is going to get crowded in trying to get into a smaller junction. So that trade-off is that link is always been at the bane of all millimeter waves and sub-millimeter wave circuit designers. And which one is better? So there's always a trade-off, because as that capacity, so the idea is that the RF needs to go across that junction resistance, RJ, because that's the nonlinearity. The CJ is not a good nonlinearity. So that's a parasitic to a large extent. So there is the trade-offs, as you can see on the bottom, input power as a function of efficiency. This is from a very nice paper. And it kind of highlights that at 10 gigahertz, you can get the efficiency at a certain power level. But at 35 gigahertz, you not only reduce your efficiency, but also you're going to need more power to write the device to circumvent the kind of the higher losses. So as far as the diode is concerned, okay, sure, you know, at W band, for sure, you need to simulate the diode in every single shape or form. So this is a cross-sectional view of an equivalent circuit model of the diode. And the diode is no longer just a capacitance and a resistance. You got the spreading resistances, you got contact resistances, you got impedance matching networks that are really close to the junction, which are your air bridge finger, for example. And then all the parasitic capacitances, which are to do with how power gets into the diode circuit. So if the capacitance of the diode is something like 5 to 10 femtofarads, if you have a capacitance of a parasitic capacitance of 100 femtofarad, you will never see the diode. So the circuit will just, the diode just will be bypassed, and you'll never, you won't have anything working. So the idea is that's why at W band, you're going to get a lot smaller in circuit size, and trying to reduce those parasitic capacitance so you can actually see the nonlinear junction. So if you look at this, this is efficiency versus input power, and this is idealized. I like this chart because it kind of shows what you're up against. So you have a VJ effect, which is a turn-on voltage for the diode. So which means that, you know, the diode doesn't turn on until a certain voltage as part of its characteristics. So you need enough input power to drive it past that to be able to get into the nonlinearity of the diode. So that VJ effect always limits some of your efficiency. And then you have the breakdown voltage effect, which effectively is saying that if I'm swinging across the IV curve with an RF swing, if I hit the breakdown voltage, the device is just going to die. So we want the high breakdown voltage, and we want a low junction voltage. As a result, then you can push the overall efficiency further and further up. So we've been working at a gallium nitride rectifier, which is no longer a diode as such, as like it's a 2-dig and 2 dimensional electron gas structure with buried gates, and these gates are fed through the vertical feed to reduce the parasitic capacitance, as we discussed. And so it does provide, so far it has breakdown voltage of 70 volts, which relieves one of the elements. And also the speed we're improving. In this particular case, you see the cutoff frequency, which is a product of the resistance and capacitance, versus breakdown voltage, which is effectively how much power it can handle. So the yellow box is where we are, and we're pushing towards the 1 terahertz range with scaling the device even further. This will allow us to actually not only switch fast at W band and of course any other frequency below it, but also push the power, increase the power. So what can you do with application space? Obviously, you know, having a wide margin of a transmitter, being able to move your transmitter and locate your receiver, whether it's ground to air, in this particular case, shipborne to air, you can create a dome of power where the UAVs will come in and get powered. I mean, this notional picture, that's what it will look like. And having a beam spread is not a bad idea. I mean, if you think about laser power beaming, that the beam gets much more collimated and much more narrow, which means that the beam has to follow the moving target or receiver continuously. And when you go to RF, you could say, okay, you know, my beam is really wide, so anybody who's in that beam, you know, help yourself to the power. So that there are trade-offs in that system power. So another thing I wanted to kind of also highlight here is that, you know, the space technologies are also opening up. So if you look at the journey to Mars, this is a NASA chart that kind of shows you what needs to be done for us to be able to get to Mars. And you can see there is anything from probes to landers to orbiters, and also moon being a kind of a staging area for that effect. And there are many, many technologies that need to be there, and how you power them is also important. So what would wireless power beaming be in a space applications? So obviously size, weight, and power is really important, because now you have to push everything into space. You no longer can rely on heavy duty transmitters on the ground and work that. So everything has to be small. Launch and survivability is important. So, you know, I mean, space qualification is expensive and hard. And then regulatory permissions that are important as to the various discussions that have been done on the as far as you know, how you can communicate in space is also important. So what frequency you would use so you don't interfere with others. And then the trade-off analysis is which, you know, obviously going microwave, you can open up the space pretty high. A millimeter wave, you can narrow the beam somewhat, and laser, you can go a long range. So between those three, you could use short range and long range effects. And remember, space long range means a long, long way. So laser power beaming is very well suited for space to a large extent. And what would you do? So, you know, rocket launch is one thing from the ground that is being tried. Well, it's been at least talked about and analysis done. And then power feeding sensors, I think that's really important, because then you don't have the wires, you don't have, and that's an important aspect. And that's been, I think, one of the major effects. And then trajectory change is like, how can I change the trajectory of a spacecraft from one orbit to another, which is a very important power consuming part. So as far as power transfer, you can see, and say, for example, if you do have a space station, and then you have the various probes, and these microsats are taking data from different things, how would you power them? How would you communicate with them? So those are ways to provide power that is very useful. Something like 100 watts would be very, very useful for something like a microsat. And the space stations are, you know, you could effectively think of it as a transmitter where you can get solar powered, and, you know, you have 20 kilowatts of solar powered, and you could build very, very compact receivers that would go on these microsats that could receive power not just from the sun, but also directionally from any other source. As far as directed energy for space rocket launches, I think that's already been looked at, and this is interesting. JPL looked at this for a while as to if you can have a high power energy radiating the fuel, and those hydrocarbons the temperature will rise, and then you start to increase your fidelity of the fuel versus the weight of the craft. As a result, you end up getting a lot more ISPs and going into space a lot faster. So that was a thought that, and is still valid. And what are the transmitters in space? A lot of the SSPAs and traveling wave tubes are there, but really, I mean, they point to the ground, and their power densities on the ground are defined very, very tightly. So you don't, communication satellites especially. So they're kind of defined in a way to be at very low power because they will be radiating a surface of the Earth and we'll be walking underneath it. So there's IEEE guidelines applied to them. But nevertheless, these technologies do fly in space, so they could be used for space-to-space work. But this is an interesting chart that shows power required for various actions within space and a duration of that power. So if you look at it, those are like 1 gigajoules and 1 terajoule lines that you see sloping in. For launch, you need like 5 minutes of, above, 10 gigajoules type of power densities, which is huge. For interplanetary, going from one planet to another, you're going to need sustained powers of well above a terajoules for hours. And then, of course, orbital is also very important. How do you change orbit? It takes a lot of energy to do so. And interstellar, which is even longer distances that could go in. So you can see the type of power you need to do these is important, and what wireless power could do for some of these applications would be of an interesting capability. So as far as what you could do is what kind of technologies so these are drastically different technologies that you could think about. I mean, if you look at just the numbers, if you had a 100 kilowatt source and you have a transmitter which is about 2.5 meters in space, you could do that without a problem. Well, it is expensive, but it's been done. And then receive antenna, like NASA is looking at sails of 250 meters wide. So that would be a very interesting angle, because if you have 250 meters, you can capture a lot of power, because power is being radiated out and from point A to point B, and at 35, 94, and 220 gigahertz, you can go push it up beyond millimeter wave and get to sub-millimeter wave. And you can see some of these lines that you can extend the range to much, much longer ranges that you could go through. So in conclusion, I think radiative power beaming has many modalities, and each modality has its own pros and cons, and no one, it really depends on the application space. If you can handle the size of the antenna and you have the regulatory issues down, lower microwave frequencies are without a doubt the way to go. If you need to go long, very long range, laser power beaming is a very nice option. If you are tactical, you want to be mobile on both sides, millimeter wave is a great option, especially as the efficiencies are going up. But the other thing is also space is a really interesting area for power beaming technologies going forward. I think we are going to have many opportunities to be able to highlight these technology overall in many different application spaces. Well, thank you very much for your attention, and if there are any questions, I will be happy to answer them.